Today we will be studying the kinetics of acid catalyzed reactions. Normally, for first order reaction, the rate of disappearance of substrate with respect to time is equal to rate constant into concentration of substrate. This is for the first order reaction. This happens when we do not have any catalyst whatsoever in our reaction mixture. However, when we have a buffer solution, in case of buffer solution, what happens? The first order rate constant K for a reaction may depend linearly on our concentration of proton, concentration of OH negative, concentration of our acid, that is let's suppose HA, and concentration of our conjugate base. Alright, so our rate constant depends linearly on these factors. Alright, where this HA is a weak acid, not a strong acid, since we know that buffer is made up of weak acids and its conjugate base. So this is weak acid and this is its conjugate base. Both of these combine to form a buffer. In other words, we can say our rate constant is equal to K naught plus K H positive into concentration of H positive, K OH negative, your concentration of OH negative, plus K HA into concentration of HA, plus Ka negative, concentration of A negative. So here this is our first order rate constant. But when our reaction is not catalyzed, so this is first order rate constant for uncatalyzed reaction. Alright, and these 4 K's are our catalytic coefficients. So if in any reaction only this factor is dominating, then we can say the reaction is subjected to specifically hydrogen ion concentration. Alright, similarly this is the case when H positive term is dominating. Alright, if we have K OH negative OH, this third term dominating, then we can say our reaction is specifically hydroxyl ion, this is not concentration, this is catalysis, specifically hydrogen ion catalysis. Okay, and if fourth term, that is our acid concentration is dominating, then our reaction is subjected to general acid catalysis. And if the last term, that is our conjugate base term, is dominating, then we can say our general base catalysis. Two mechanisms has been proposed for the acid catalyzed reaction. So first of all, we will take the first mechanism in which our substrate reacts with an acid and gives us substrate proton complex and our conjugate base. This is K1, this is K inverse. Then this reacts further with water to give us product, and this back. This is K2. Okay. Now if we have to write down the rate of reaction, that is rate of formation of product with time, what we will do, we will write in terms of the second step, and it will be equal to K2 concentration of SH positive and concentration of water. But in this case, since this is our acid which is acting as a catalyst, so this will be very small quantity as compared to your reaction mixture. So this is very small, and this is giving a intermediate SH positive, so the concentration of SH positive will also be very small, and when compared to our solvent, that is H2O, it can be neglected. So in this equation, we can say our solution is diluted. Okay, so this reaction, instead of being second order, is a pseudo first order reaction, and our reaction rate will become K2 SH positive. Alright, now we do not know the concentration of SH positive, so how do we find that? In order to find that, we will apply steady state approximation for SH positive. Alright, and what does steady state approximation says? It says that the rate of formation of intermediate is equal to the rate of decomposition of the intermediate, or in other words, the rate of change of concentration of intermediate with respect to time is 0. So now what we can do, we can take the rate of formation of intermediate minus rate of decomposition of your intermediate. So the intermediate is forming in the first step in the forward reaction. So our rate for the forward reaction is K1 concentration of substrate and concentration of AH positive. Now since the SH positive is decomposing in the backward reaction, so we will put a negative sign and our rate constant into concentration of your reactant for the backward reaction. So backward reaction is going in that direction, so these two are reactant for our backward reaction. So I have written minus K inverse into SH positive into A. Now in the second step, SH positive is decomposing to form your product. So we will write K2 SH positive. Again, here we are not writing the water because it's a pseudo first order reaction. So this we got. From this we will do our mathematics and find out the SH positive. I am not doing all the calculations, I am directly writing down the value of SH positive. So this is K inverse A plus K2. So this is value of our SH positive. Let's suppose this is our first equation and this is our second equation. By putting the value of SH positive from second to the first, we'll get the rate of reaction. So our rate of reaction in this case become K1 K2 S AH positive and K inverse A plus K2. Alright, so let's say this is our third equation. Now two cases arises. We have two terms in the denominator. First case is when your K2 is much greater than K inverse A. In that condition, what happens? Or in other words, what does this means? This means the backward reaction, the first step is slow as compared to your second step. Alright, so in that case we can neglect the K inverse A, and in the denominator only this term will be remaining. So our rate becomes K1 K2 S AH positive divided by K2. These K2 cancel out and our rate becomes K1 concentration of substrate plus acid. Alright, now what was this term? Your this is acid. Here in this case we have taken acid as AH positive, so don't get confused. This positive sign I have intentionally put here so that I can show the shift of your proton. Alright, so this is our acid, and here we had acid term, acid term here. So if this term is dominating, then our reaction is general acid catalysis. So in this case our reaction is following general acid catalysis. Alright, now comes the second case. Second case is K2 is much smaller than K inverse A. In this case, if you have this type of condition, this suggests that your backward reaction is faster as compared to your second step. So your rate of reaction becomes K1 K2 S AH positive and your K inverse A. Alright, now we know that AH positive decomposes to give conjugate base plus proton. Alright, this much we know. If we have to write down the chemical equilibrium, this is equilibrium constant. So our equilibrium constant for this reaction will become concentration of conjugate base, concentration of proton divided by your acid concentration. So on manipulating this, if we have to find out the value of this, what will be the value? The value will be H positive divided by K. So here this K is actually equilibrium constant, not the reaction rate constant. So this is our fourth equation, and let's suppose this is fifth. So putting the value of this into fourth equation, we will get our rate as dP by dt is equal to K1 K2 concentration of S and H positive divided by K inverse and capital K. All of this is constant. So in this equation you can say the dominating part is your proton concentration. So this reaction is actually specifically proton, or you can say hydrogen ion catalysis. All right. Now comes the second mechanism. Second mechanism is slightly different. In this, the substrate reacts with your acid. The first step is similar. In this you are getting SH positive and your conjugate base. Now this further gives us product plus your acid back K2. So in this mechanism, if we have to write the rate of reaction, it will become K2 SH positive and A. Again, we do not know the concentration of SH positive, so we will apply steady state approximation for SH positive here, and this will become the change in concentration of your SH positive with time is equal to 0. And if we have to write down the values of rate of formation of your intermediate and rate of decomposition of intermediate, it will be K1 S into AH positive minus K inverse SH positive A minus K2 SH positive A. Alright, and from this, after doing my mathematics, SH positive was equal to K1 S AH positive divided by K inverse plus K2 A. So if this is our first equation, this is our second equation, then rate of the reaction becomes K1 K2 SAH positive divided by K inverse plus K2. Now the AA we had, these two cancels out. So what we are getting, K1 K2 divided by K inverse plus K2. This is all constant value of concentration of substrate and concentration of your acid. So from the third equation you can clearly see this is your acid. So this reaction is this mechanism is following general acid catalysis. All right, and this is a derivation for our acid catalyzed reaction. Similarly, you can do the reaction for base catalyzed reactions also.